Okay, so before proceeding, let's do some stuff about torsion representations. Okay, so torsion representations. So like, okay, let me just torsion representations. Okay, so this is representations of the Galois group on torsion of abelian varieties. Okay, and so, okay, so here's like a key question that one can ask, right? Is so define, LL to be L adjoin the L torsion of an abelian variety. Okay, so is the ramification of the Galois representation we could do rho L. Okay, this is from GL to the automorphisms of this abelian variety over Q bar, right? The same as the ramification of the field. Of LL over L. So more precisely, is it the case if, so let W be a place of LL. Okay, let's say W be a place of LL, let's say dividing V a place of L. Okay, is it the case that EW over V is greater than 1 if and only if rho L IW or I V bar over V is not equal to 0. Okay, so okay, so let me just let's recall that that okay, so this was maybe so this is rho L. Okay, so this is true. So recall that a representation. So given rho from GL to let's say the automorphism of some vector space, right? We say rho is ramified if the image of at let's say a place V and V of L, so this is the place of this, if the image of the inertia over, and you pick some place here, is not 0. And it's unramified if the inertia goes to 0. Okay, so this is what we have. Okay, so this is the question that we have. Okay, so, all right. So let me just clarify some things now. So if, okay, so now let me just go a little bit and start talking about these things. Okay, so let A have a projective model. So A is an abelian variety, and so let A be embedded into Pn of say L for some L. Okay, and so then we define. So how do we define? I just want to clarify how we define this thing, right? So it's A adjoin, or sorry, it's L adjoin the coordinates of A L of Q bar in the embedding, right? And so the claim that I want to make is that this is independent of the embedding, right? LL is independent of the model, right? Okay, so model meaning the choice of a projective embedding, the choice of coordinates. So let me give the proof. Okay, so suppose phi from, so we'll denote A by the embedded model. So let's say A to A prime is an isomorphism over L of models defined over L. So then it's given by polynomial equations over L, right? So let okay, so let let's let LL and LL prime be the fields determined by these models, by A and A prime respectively. Okay, then clearly the coordinates of A prime L Q bar are contained in LL. Why is this? Right? Well, it's because that here you're going to have some coordinates, right? And they're going to map to all the coordinates of this thing, right? So by some L, so there are going to be some polynomial combination of the coordinates on L sub L. Okay, and so all right, it's because they're just polynomial functions, all right, and so so the opposite also holds. Right, so and so we have one contained in one and the other one contained in the other, so they have to be equal. Okay, so it doesn't matter which model we pick. Okay, so let's do another lemma. So fix Q bar in algebraic closure. I guess I'm always fixing an algebraic closure. I don't know why I stated this. Okay, so and then consider the Galois representation where we have rho L, so from GL to the torsion. Okay, then we have the following. We have that LL, this is the thing where we adjoin the torsion, is equal to L bar, right, kernel of rho L. Okay, so this is what we have here. Okay, so proof. Okay, so let LL prime be this L bar, this kernel version. Okay, so we're going to have that LL is going to be contained in LL prime. Okay, how is this? So we need to show for each alpha in LL, we need to show, let's say 4, but each alpha in LL is invariant under sigma in the kernel of the map. Okay? So we know that for every A, which is A0 up to AN in ALF, so here I'm considering some embedding, and every sigma in the kernel of rho L, we have that sigma of A is equal to A. Or, okay, and then let's continue this on the next page, that sigma of AJ is equal to AJ for J is 0, 1, all the way up to N. Okay, so all of its coordinates, all of its component functions are fixed. Okay, and since LL is L join A0 up to AN, where A0 up to AN is in AL L bar, right? So okay, so so we'll say Q bar. Okay, so so what we've done is we've adjoined all the torsion points, right? So we know that LL is fixed under the kernel. Each sigma in the kernel. Okay, so conversely, we need to show that that the fixed field is contained in the torsion, and this one's you just have to think about it a little bit, but you just use the fundamental theorem of Galois theory. So we have this. So we'll take this. So this is the set of sigma in GL, such that for all elements of this thing, sigma alpha is equal to alpha. Okay, so this is the definition of the fixed field. Okay, so this, or the Galois group of L bar over L. Okay, and this is equal to the set of sigma in GL, such that for all A in AL L bar, sigma of alpha is equal to alpha. Okay, so this is this is what we talked about before. Like you fix the torsion point if and only if you fix the field, and by definition, if you're fixing a torsion point, this is the kernel of this map. Okay, and that's that. All right. Okay, so maybe this is even an easier way of doing this, right? So you just think of it this way. This does both, really, by the Galois correspondence. Okay. Okay. So I have another thing where I just check this equality, but right now it seems so clear to me. And I'm not going to do it. Okay. So yeah, it's the same thing. Okay, so so let's do a corollary. So a corollary of this thing. Okay, and this is interesting. Is that G of LL over L is isomorphic to the image of rho L and of GL, and then we take the automorphisms of, okay, and so here I'm just abbreviating, this is also the Q bar points, okay, so I'm omitting that there, okay, so so let's do the proof, so I mean this is silly as well, this is the fundamental theorem of Galois theory. Of Galois theory. Okay, and the first isomorphism theorem, right? Okay, so maybe I can just do it here. LL over L isomorphic to G of L bar over L, G of L bar over LL, and this is G of L bar over L modulo the kernel of rho L, and this is isomorphic to the image of rho L. Okay, so this is the first isomorphism theorem, and this is a fundamental theorem. Fundamental theorem. Okay, so all right. So by the way, while we're here, So there's this Serre's open image theorem. So it says that so there's a theorem. This is called Serre's open image theorem. Okay, and it says that for an elliptic curve without complex multiplication, the image of rho infinity from GF, so let's say GL. Okay, so E is an elliptic curve over L. Let's say over number field. Okay, to the automorphism group of T, which is the full Tate module. That's the inverse limit of the torsion, right? That this is open. Okay. All right, and so the topological condition, right? So this thing implies this theorem here implies that the image of rho in so rho L, right, is equal to GL2 FL for L sufficiently large. Okay, so that there exists some n such that for all n greater than L, we have this. In the conjecture, there's a conjecture which is the following. It says that so for all L number fields, right, one, that there exists some maximum L in the natural numbers such that, so this is a uniformity statement such that for all E over L without CM complex multiplication, the image of the Galois representation is the full thing. Okay, and then the theorem, the conjecture is further, is that when we look at Q, L max is 37. Okay, so there's a very specific one bound here when you get the full thing. Okay. Yeah, so the idea is that so what you can do is you can show that if an elliptic curve has an L torsion point, a rational L torsion point, these are ideas of Mazur, then the image of the mod L representation, that's rho L, is not surjective, and that works for L less than 7. And then if E admits a Q isogeny, right, then the thing's not surjective, and it works for L less than or equal to 17 and L is equal to 37. The converses are not true. So it's like if you have a torsion point, notice that you can like mod out by the torsion point, and that gives you an isogeny. Okay, and so this is kind of what's going on. Anyway, that's this. I mean, the silly part of the mod L representations. Okay, and now I'm going to talk a little bit about some the good reduction of abelian varieties.